This is a follow-up to a video that I made about why, or the long version of how we deal with complex slash imaginary, in this case, eigenvalues, and how we get to the quick solution and how it lines up with the long version of the solution. Now I'm going to do just one example in the quick way so you can see how to do it. So this one is, and once again, this one's only imaginary, but the same process is used with complex ones. So lambda squared. My trace is 0, so plus 0 lambda. And then when I multiply here, I get negative 1. And then when I subtract this, I get plus 5, which gives me plus 4 equals 0. Well, that is lambda squared equals negative 4, which gives me lambda equals plus or minus 2i. So, as I said before, we're only going to look at one of them. I am going to take lambda equal to the positive 2i. Why do I do that? Because it gives me an Euler's formula that doesn't have a negative in it. So when I plug that into the matrix up here, I get 1 minus 2i, negative 5, 1, negative 1 minus 2i. And in this case, I think you should see that we like to keep things positive if we can, just to avoid negatives and errors. So, normally I say switch and negate, right? So what we're going to do is negate this one and switch it with that one. So I get 1 plus 2i and then 1, and I have as many positives as possible, so I'm less likely to mess this up. So next thing I do, I take that vector, and I go 1 plus 2i, 1, and I'm going to multiply it by e to the 2i t, which is just 1 plus 2i, 1, and the e to the 2it, honestly, you don't even need to write this once you get in the habit of this stuff, but that at least connects it with the ideas from above. That is just cosine of 2t plus I sine of 2t. Again, the reason why I chose the positive 2i here was so that I would get a plus sign here. If you take the negative right there, then you have to do a negative there. It does give you pluses here, though. Your choice. So, what does that look like? That is equal to, I'm going to write it out in a long form so that you can really see it. In the top row, I have 1 plus 2i, and that gets multiplied by cosine of 2t plus I sine of 2t. Close. And then in the bottom, I have a 1, that's this, times this same thing. So times cosine of 2t plus I sine of 2t. Is that correct? And brackets for the vector. So what is that equal to? Well, this is like foiling, right? This by that, this by that, and then this guy by that, and this by that. So what's that give me? I get 1 times cosine 2t, which is cosine 2t. I get 1 times I sine t, so plus I sine 2t. And then I get 2i times that, 2i cosine 2t. And then I get 2i times I sine t. The I gets squared, gives me a negative. So it's negative 2 sine 2t. From there, the bottom is simple. There's not much to do. Just multiply by 1, so it's the same thing. So I get cosine 2t plus I sine 2t. From here, imaginary, 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 and real, real, real. So the greens go into one vector, and the reds go into another vector, and those are my two solution pieces. So it's my solution, x of t, is equal to c1 times plus c2 times this. and all the green ones go in here. So I get cosine of 2t minus 2 sine 2t, and then cosine 2t. And then in this one right here, I get my the I pieces without the i's, right? So I get the imaginary components without the i's. So it gives me sine 2t plus 2 cosine 2t, and in the bottom, sine 2t. And that is, if I were to zoom out up here, all of the highlighted pieces from this long example I used to show you how to do it. So imagine how much longer this would be if we had to do all of the work that we took here. So I hope that two things. One, I hope you can see what happens here and how it leads us directly to this. So I hope you see why we have this system where we just only do one eigenvalue and break it into real and imaginary components, and that's our solution. One, I hope you see why that works, at least from an example perspective. And secondly, I hope you appreciate the amount of work that gets cut out by using this shortcut. Cool, thanks. See ya.